So we're going to move on now to our next type of chemical reaction. And these are called oxidation-reduction reactions. An oxidation reduction, also known as a redox reaction, is a chemical reaction in which electrons are transferred from one reactant to another. So oxidation is the loss of electrons, and reduction is the gain of electrons. So let's look at an example of a redox reaction. Here I have zinc solid reacting with copper ions that are in solution. In my image here, I literally have a piece of zinc metal that I'm putting into a solution that has copper ions in it. Copper ions, fun fact, are blue when they're in solution. So if you ever see a blue solution in chemistry lab, it's probably a copper solution because they turn blue. Okay, so what's happening is the zinc and the copper are essentially changing places, right? Copper's a metal and zinc's a metal. What's going on is that zinc metal is made up of individual zinc atoms, and the copper ions want to become a solid. So they're changing places, and in order to do that, they are exchanging electrons. So we start with copper ions and zinc solid, and what happens is because they have a difference of 2 electrons, zinc says, I'll give you 2 of my electrons, and I'll become zinc 2+, right? A loss of 2 electrons makes you a cation with a 2+ charge. And that means if I give you those 2 extra electrons, copper, you'll become copper solid. And over time, what happens is with each zinc that goes into solution and a copper comes out, we keep seeing that transfer of electrons, right? We see it happening up here as well as down here. They're literally just giving them away, transferring them from one metal to another. And it ends up where our zinc solid is now copper solid and a bunch of zinc ions. So they literally changed places. So through the exchange of electrons, we went from zinc solid to zinc ions that are aqueous in solution. And in turn, the copper ions that were in solution became copper solid. So they changed phase. And the only way they can do that is if they transferred electrons. So, again, to reiterate, zinc, when it's a solid metal, it has all of its protons and its electrons. So it has a 0 for a charge, right? It's neutral. Zinc would rather be in solution, and copper would rather be a solid. So what happens is zinc says, I'll give you 2 of my electrons, so it loses 2 electrons and becomes, here's that line, becomes zinc 2+. The electrons have to go somewhere, so the copper, which has a 2+ charge, is like, I'm missing 2 electrons. I'll take those 2 electrons that you're giving away, and I'll become copper solid. Because if we add 2 electrons to a 2+ cation, it becomes neutral with a charge of 0. And any metal with a charge of 0 is a solid. Okay, so we see copper ions that were in solution becoming solid, and we see zinc solid turning into copper ions in solution. So what's happening here is we are exchanging electrons. Oxidation is the loss of electrons, and reduction is the gain of electrons. So since zinc lost electrons, it gave them away, it lost 2 electrons, it is being oxidized. There we go. And since copper accepted those electrons, it gained additional electrons, it is being reduced. So oxidation and reduction reactions, again, are the exchange of electrons between our 2 reactants, and oxidation is the loss of electrons, and reduction is the gain of electrons. A redox reaction overall is the sum of an oxidation half reaction and a reduction half reaction. So half reactions are just showing for that specific metal or that specific compound what is happening to the electrons. So it's really just showing half of the reaction that's going on. So in our zinc and copper example that we just looked at, we said that zinc was being oxidized and copper was being reduced. So the oxidation half reaction shows that zinc solid turns into zinc ions, and because it lost 2 electrons, the product of that oxidation is the zinc ions and the 2 electrons that it lost. It decomposed into an ion and 2 electrons. The reduction half reaction shows that copper gains 2 electrons, so if it's gaining, those electrons are going to be on the reactant side because it's part of that reaction. They need to be there for the reaction to be complete. So it gains 2 electrons and turns into copper solid. These are half reactions because they're only showing half of the reactants and what's happening to that specific reactant. So we can then add those 2 half reactions together to get the overall redox reaction, which is copper aqueous and zinc solid turns into zinc aqueous and copper solid, which is the example we saw on the previous slide. When we do this, we see that those electrons that are being transferred cancel out, just like our ionic equations. Anything that's similar on both sides, or anything that's the same on both sides of those arrows, are going to cancel out. Since the 2 electrons from the zinc had to go somewhere, they can't just float around in solution, right? We can't have just rogue electrons everywhere. So they need to go to the copper. So they should be canceling out in the overall reaction. We would not have any extra electrons left over in our reactions. Okay, we have some special terms for what's doing the oxidation and what's doing the reaction. So zinc, which was being oxidized in our reaction, functions as a reducing agent because it provides the electrons for copper. So it allows the reduction to happen. So whatever's being oxidized is then the reducing agent. It provides the electrons for the reduction to happen. Copper then functions as the oxidizing agent. So copper was being reduced. So it functions as the oxidizing agent because it effectively removes the electrons from zinc. So it accepted those electrons. It gave the electrons a place to go, allowing the oxidation to occur, allowing zinc to lose its electrons. So whatever is being reduced is the oxidizing agent. And that is always what's going to happen. If it's being oxidized, it is the reducing agent. If it's being reduced, it is the oxidizing agent. We have some mnemonic devices that we can use to remember how the electrons are being transferred in oxidation reduction reactions or redox reactions. The first one is oil rig. Oxidation is loss of electrons, and reduction is gain of electrons. So this one, oil rig, is talking specifically about the electrons. It just doesn't have a term in there that specifically says electrons. I personally like oil rig over the other one, but whatever one speaks to you more that allows you to remember this, use it, okay? So the other mnemonic device is Leo the lion goes grr. So we have Leo, L-E-O, lose electrons oxidation. And then we have grr, gain electrons reduction. So Leo the lion goes grr is a little bit longer, but at least it reminds you that it's the transfer of electrons in oxidation and reduction. So whichever one you choose to use, it works the same way. They're telling you the same thing. Oil rig or Leo the lion goes grr. It just depends on what makes more sense to you. So let's practice. So for the balanced redox reactions, I'm going to change this. So feel free to change this in your own lecture note pack. I don't want to write the half reactions. We'll get to that later in this. And we're not going to identify I guess we can identify the redoxidation or reducing agents. But what I want us to do first is just identify what is being oxidized and reduced. Okay, so I'll put our little mnemonic devices up here. Oil and rig, and Leo and Gur. Okay, so we're not going to write the half reactions just yet. We'll do that more so in the later half of this lesson when we talk about overall reactions. So let's just not write the half reactions just yet. So for these balanced reactions below, identify what is being oxidized and reduced, and then identify the oxidizing and reducing agents. So the first thing you're going to want to do when you're looking at these is think about the charges, right? The charges are going to tell us how those charges are changing, where the electrons are going. So we need to look at the charges of everything in these compounds. So iron by itself is a metal, so it has a charge of 0, right? We know that. When we just see iron metal, it's coming straight off of the periodic table. It hasn't lost any of its electrons. There's no charge on there. Therefore, it has a charge of 0. Oxygen gas is also the elemental form of oxygen, so it also does not have a charge. There's no ion there, so it also has a charge of 0. On our product side, we have iron 3 oxide, and that's an ionic compound. It's made up of a metal and a nonmetal. So we know we can separate this guy into its 2 charges. So we do a little reverse crisscross. The 3 came from the iron, the 2 came from the oxygen. So we get Fe 3 plus O 2 minus. Okay, so now we want to look at how those charges are changing. Well, to go from iron to iron 3 plus, what happened to my electrons? Well, if I became a cation, I had to lose some of my electrons, right? I lost electrons in order to turn into a cation. So how many electrons did I lose? Well, I went from a 0 charge to a 3 plus charge, so I should have lost 3 electrons. For oxygen now, oxygen went from 0 and it turned into oxygen with a 2 minus charge. In order to go from a neutral charge to a 2 minus charge, in order for it to get more negative, we had to add on more electrons, right? An anion is the gain of electrons. If I have more electrons than protons, it's more negative. So this one gained electrons. So oxidation is loss, reduction is gain, or lose electrons oxidation, gain electrons reduction. Well, lost electrons, oxidation, iron lost electrons, so Fe lost electrons, therefore it's being oxidized. Oxygen gained electrons, therefore gain electrons reduction, it's being reduced. We next want to determine what the oxidizing and reducing agents are. Well, we said whatever is being oxidized is the reducing agent. So iron is the reducing agent. And whatever is being reduced is the oxidizing agent. So they're just opposites. You just got to remember that they're opposites. Whatever is being oxidized is allowing the reduction to happen, therefore it's the reducing agent. Whatever's being reduced is allowing the oxidation to happen, so it's the oxidizing agent. Our next example is then Cl2 reacting with sodium bromine, creating sodium chloride and bromine. Well, we have to look at our charges first. So we have chlorine gas, Cl2, and since that's its elemental form of chlorine, it has a charge of 0. The same goes for Br2, it has a charge of 0. NaBr and NaCl are both ionic compounds, so they're made up of ions. So we know Na has a positive 1 charge, and Br has a -1 charge. On the product side, Na again has a +1 charge, and Cl- has a -1 charge. So, sodium did not change on either side of the arrow. Okay, its charge did not change, it remained as sodium plus. So we're going to define Na plus as a spectator ion. It follows the same definition of spectator ions in our previous lesson, where it did not change from reactant to product side. It's the same on both reactant and product sides, so it is not going to be oxidized, it's not going to be reduced, it is just a spectator. So let's look at chlorine and bromine to see which one is being oxidized and which one is being reduced. We have Cl2 that turns into Cl-. Well, if I went from a neutral charge of 0 to a -1 charge, I had to gain electrons in order to do that, right? I had to add on some electrons. For balancing, this would be a 2, so that would end up being 2 electrons. Don't worry about balancing that, and right now we'll talk about that later. So chlorine gained electrons. If we look at bromine, it went from Br- to Br2. Again, we'll just balance that for fun. Okay, Br2 has a 0 charge, Br- has a -1 charge. So in order to go from a negative charge to a more positive charge, we had to lose electrons, right? I had to give away electrons in order to get back to neutral. So I lost some electrons there. So, lose electrons, oxidation, lost electrons, which means Br lost electrons, so it's being oxidized. Chlorine gained electrons, gain electrons, reduction. So Cl gained electrons, so it's being reduced. If it's being reduced, it is then the oxidizing agent. And if it's being oxidized, it is then the reducing agent. To clarify one point specifically for your ALEX homework, I do believe that they ask you, when they ask you to identify the oxidizing agent and the reducing agent, since Br is what's being oxidized and therefore is the reducing agent, the entire the entire compound of NaBr would be considered the reducing agent. So they're looking for the full formula of where that came from. So since Br- came from NaBr, the reducing agent would be NaBr. Other textbooks, other places, they say the reducing agent could just be the ion that's changing, and we don't need to worry about the spectator ion, but I do believe your ALEX homework does want you to put the entire compound formula in when it asks you for the reducing agent and the oxidizing agent. So, for example, chloride, you would actually put in Cl2 as the oxidizing agent, not just Cl. So, keep that in mind when you're being asked on your homework for the oxidizing and reducing agents. They want the full compound, not just the ion that's changing.